Video we'll be modelling with the Poisson distribution. The first thing that we're really going to get into is when it's appropriate to use the Poisson distribution. Firstly, when the events occur at a constant rate. Secondly, when the events occur at a single rate, and when the events are independent from one another. And we'll go through two examples, and we'll kind of explore this and it'll become a lot more clear. Okay, so the first example is an internet service provider has a large number of users regularly connecting to the internet. On average, 4 users every hour fail to connect to the internet at their first attempt. So this kind of tells us the layout of the Poisson distribution. It will be x, po, 4, and we always have to define where x is equal to the number of users that fail to connect to the internet on their first attempt. In an exam, you'll always have to define the Poisson distribution because you usually get a mark for that as well. Okay, so give 2 reasons why a Poisson distribution might be a suitable model for the number of failed connections every hour. Okay, first of all, if we look at these conditions above, the events occur independently from one another. One failed connection doesn't cause another. So independent. But also the events occur at a constant rate. It says on average 4 users failed to connect to the internet on their first attempt every hour, and this is a constant rate, and so we can jot this down. So find the probability in that a randomly chosen hour 2 users failed to connect to their first attempt. So we have x po 4, p x is equal to 2. We can plot this into our calculator, or we can use our formula e to the minus lambda to the x over x factorial. In this case, it would be 0.1465. Okay, so for part II, the probability that more than 6 users failed to connect to their first attempt, that is probability x is greater than 6, which is equivalent to 1 minus the probability that x is less than or equal to 5. If we plug this into our calculator, we get 1 minus 0.88933, which is equal to 0.11067 or 0.1107. Okay, so for C, find the probability that in a random 90-minute period. Okay, so we realise that for the first part of the question we're talking about an hour, now we're talking about a 90-minute period. And so instead of using x is equal to 60 min, we have 3 over 2x is equal to 90 min. We can also recall 3 over 2x is equal to y. So we can create a new distribution where y po 6, because 3 over 2 times 4 is equal to 6. And so for a 90-minute period, on average, we'll have 6 failures. Okay, so find the probability that in a random 90-minute period, 5 users failed to connect to their first attempt. So that's a probability that y is equal to 5. And if we put this into our calculator, we get 0.1606. And then for the second part of the question, find the probability that in a random 90-minute period, fewer than 7 users failed to connect at their first attempt. So P y is less than 7, which is also equal to the probability that y is less than or equal to 6, which is equal to 0.6063. Okay, so for the second question, it's a bit more tricky because we end up using 2 distributions. So for part A, a company produces chocolate chip biscuits. The number of chocolate chips per biscuit has a Poisson distribution with mean 5. So as usual, we want to write out our distribution and we want to define it. So x is equal to the number of chips per biscuit. So find the probability that one of these biscuits selected contains fewer than 3 chocolate chips. So that's probability that x is less than 3, which is equal to the probability that x is less than or equal to 2. If we plug this into our calculator, then we get 0.1247. For part B, a packet contains 6 of these biscuits selected at random. This is no longer Poisson distribution, but we're using a binomial distribution. So y, b, 6, because this is the n value of a binomial. If you notice, a binomial is often in the form of n and p, so this is the number and this is the probability. Find the probability that exactly half of the biscuits in the packet contain fewer than 3 chocolate chips. If you notice the first part of this question, we were talking about things that contain fewer than 3 chocolate chips. We got the probability is 0.1247, and we can use this in our binomial. And then it's just a standard, what's the probability of y equaling 3, because it says exactly half, so half of 6 is 3. And if we plug this into our calculator, we get 0.02598, which is equal to 0.0260. So these are a few problems solved from the textbook, modelling with a Poisson distribution. In the next video, we'll probably be looking at the mean and variance of a Poisson distribution.